Today we are learning about geometric series. And here is the formula that we will be using to find the partial sum of a geometric sequence. Here we have the first term in our sequence, and then it's 1 minus the common ratio to the nth over 1 minus the common ratio. So for example, if we wanted to find the sum of this geometric sequence, and let's say we just wanted to find the sum of the first 20 terms. The sum of the first 20 terms would be 10 times 1 minus, r here is 1/2. We can find that by dividing consecutive terms. 5 divided by 10 is 1/2. So 1 minus 1/2, that will be raised to the 10th over 1 minus 1/2. And now some of these we can do by hand, but I am going to use my calculator for this. And I get 5115 over 256. So if we added the first 10 terms of this sequence, this is the sum. Now there's one thing that we have to be very careful with. I'm going to show you with these two examples here. So here we've got a geometric sequence, same sequence over here, and we're going to use our formula. And we're adding up 12 terms. The first term, if we substitute 1, we get 4 times 0.3 to the first. So that is 1.2 times 1 minus r is 0.3 to the 12th over 1 minus 0.3. And I'm going to round this off. You should get something like 1.71428 and so on. So now with the second sum, notice that we're not starting at I equals 1, we're starting at I equals 0. So if we're using the same formula, our first term we're going to get by substituting 0, not by 1. So here we have the sum. Now we're adding up 13 numbers. If we go from 0 to 12, including 0 and 12, that's 13. The first term is going to be 4 times 0.3 to the 0 power. That's just 4. We've got 1 minus 0.3 to the 13th over 1 minus 0.3. And that turns out to be 5.71428. So notice here the difference. We've got a difference of 4 between these two summations, which makes sense because we added this additional term here when I equals 0 to this sequence. You also want to be careful that you're using the correct formula for the correct series. So here are 3 examples where we would actually use 3 different methods. So this first summation here, notice that this is arithmetic, that it's linear. So we would want to use this formula. We're adding 100 terms. The first term, we substitute 1, we get 2 plus 3, which is 5. And the nth term, we substitute 100, we get 203. And that turns out to be 10,400. But this sequence here, this is geometric. Notice the exponential relationship happening. So for this summation, we would want to use the formula that we just learned. So the sum of the first 100 terms. The first term we'd have to plug in 1. We get 4 times 1/2 to the first. That's just 2. For 1 minus 1/2 to the 100th. For 1 minus 1/2. And then this third one here is not arithmetic or geometric. So in order to find that sum, we would have to add 1 over 1, 1 over 2, 1 over 3, all the way up to 1 over 100. So for our purposes, since this series is not geometric or arithmetic, we can't apply a formula to it. So imagine if you wanted to find the sum of all of the numbers of a geometric sequence. That is, to find the sum of infinitely many numbers. Well, imagine here that n is going to infinity. Right? N is infinitely large. So what happens? As n gets infinitely large here, the base, which will always be some value between 1 and -1, would continue to get smaller. So as a power gets larger and larger, this number would get smaller and smaller and smaller. Think of 1/2 squared, then 1/2 to the third power, then 1/2 to the fourth, and so on. That fraction gets tinier and tinier and tinier, to the point where this is getting infinitely close to 0. So our formula becomes, for infinitely many terms, your first term times 1 minus 0 over 1 minus r. And we can simplify that to be 1 over 1 minus r, or just the first term over 1 minus r. So here are two examples. Notice we're adding infinitely many terms. We've got a geometric sequence here and a geometric sequence over here. So our formula looks like this. The first term, we'd have to substitute 1. We get 1 minus 1, which is 0. 0.6 to the 0 is 1. And 4 times 1 is just 4. Over 1 minus r is the base. That's 0.6. So this is 4 over 0.4, which is just 10. So imagine that if we added all of these terms in this infinite sequence, we would end up with 10. All right, trying our second example here. Now again, we have to be careful because we're not going to find the first term by substituting 1. We have to substitute 0. So 1/2 to the 0 power is 1. So we have 1 in the numerator. For 1 minus r is 1/2. That's 1 over 1/2, which is equal to 2. So what this means is if we add up infinitely many terms in the sequence, this would be 1 plus 1/2 plus 1/4 plus 1/8, and so on. Infinitely many numbers that would be equal to exactly 2. So here are the two formulas that we learned about today. The first is our nth partial sum. These are both for geometric sequences exclusively, geometric sequences. This is for a partial sum. That is, there's a first term and a last term. This is for an infinite sum, which does not have a final term. Remember, you're adding up infinitely many numbers when you're using this expression here.